To set up the fault injection experiment, we first have to adopt the test bench service. The test bench verifies the behavior of Selene prototype in presence of faults. And this is done on the request of the Davos tool. Davos submits a test command to the socket of the test bench. The test bench in turn runs some workload on the Selene platform. It then verifies the processing results, and then it responds to Davos with a status message about the observed failure mode. How the test bench communicates with the Selene, it depends on the workload. In this example, the workload communicates with the test bench via a small memory buffer on the board side. This buffer basically contains a start flag or a semaphore, which is followed by the control loop of the workload. And when the semaphore gets unlocked by the test bench, the workload starts executing some kernel. This might be a matrix multiplication, an AES encryption, or maybe some other kernel from the examples that we have provided in the repository. Then for the obtained results, the workload calculates the hash sum, the CRC32. This hash sum is placed to the output buffer, and it also writes a ready flag to indicate that the workload has completed. This hash sum and the ready flag are checked by the test bench, so to determine the failure mode. Saying the test bench will return the masked mode if the Selene has responded in time and the result was correct. It will return a fail or data corruption if it has responded but the result was incorrect. Or the test bench may also return hang or crash if the Selene has not responded at all. On the second step, we configure the fault load and some other Davos parameters. Some generic parameters like output directory to export the fault injection report and the input directory with the Vivado project file. So now the fault load. Let's say we first want to inject faults into the lookup tables of a certain Selene component. For instance, into the first processor core. And we select a sample of 5,000 faults. So we navigate to the Vivado project to observe the design hierarchy. We can see here a fault injection core, which is isolated in a P block far away from the rest of design. Then we locate the processor cores, so we can see each of the cores in a dedicated P block. Also, these P blocks are only needed for the area-based injection. I will also comment this later in this demo. So we allocate the core 0, copy its design scope, and we paste this design scope into the configuration file. So the rest of parameters we keep at default settings, and we save this file. So once we have adjusted the configuration, we can now run the fault injection experiment. We open a Linux terminal, we navigate to the Davos directory, and we start the FFI tool with this configuration file on the input. So now we only need to wait for the completion. We can see that Davos parses the netlist, bitstream, essential bits. It reports the amount of lookup tables in the targeted design scope. Then it generates a fault list of 5,000 faults. They are randomly sampled from roughly 3 million of load bits in the core 0. Then it starts the injector application on Microblaze and also the test bench on Germon. And then it processes the fault list using these two services. At the end, we can see the result in a distribution of failure modes. Basically 0.8% of failures and 0.33% of hangs. And we can also examine which faults have led to data corruption and to hang failures. And now we can examine the detailed fault injection log from the CSV file. So we can filter the results by the fault target, by failure mode, or by some other attributes. For instance, we can select the critical faults that have caused the system to fail or to hang. To test the fault effects in the rest of essential bits, including routing, we configure another experiment. In this case, we specify the P block or rectangular area on the chip in terms of grid coordinates of the bottom left and the top right tiles of the P block. We can check these coordinates in the Vivado floor plan. And as a target logic, we select the type 0 frames of the configuration memory. And again, we open the Linux terminal and invoke Davos FFI tool. Davos reports 15 millions of essential bits in the area of core 0. And this is roughly 5 times more than we have previously had in the case of lookup tables. So we wait for the completion of experiment, and we can see at the end somewhat higher failure rates this time. All collected results automatically saved to the database. We can query and visualize these results using Davos web interface. We open a web browser and we navigate to the report page. It has several widgets. The top left widget to query the results attending to different filters. For instance, we can query bit flips and lookup tables. For these results, next widget shows the percentage of failures and hangs, and also other failure modes, and also the sampling error. The top right widget shows how much each design component contributes to these failure rates. In this case, it is the integer unit, and in particular the execute stage of the pipeline. The widget below illustrates the distribution of weak points on the design tree in a slightly more convenient way. And we also have the table below that provides the details of each injection run. And then we can query the results for the essential bits for the type 0 frames. And we can see that in this case, both the failure rate and hang rate are much higher than in case of loots. This is probably because the routing bits are more critical than the loot bits. Okay, that's all. Thank you for your attention.